We're going to take a look now at nuclear half-life. And when radioisotopes decay, each isotope decays at its own rate. And we'll take a look at how to calculate what those half-lives are and learn a little bit more about half-lives. Definition of a half-life of a nucleotide or a nuclide or a radioactive isotope, those all mean the same thing, is the amount of time it takes for half of the original quantity to decay. The symbol for half-life is T with a 1/2 subscript. There's a whole range of half-lives for various radioactive isotopes. Polonium-214 has a very short half-life. It's 1.5 times 10 to the negative 4 seconds. Near the other end of the spectrum is radioactive uranium-238. It's the naturally occurring isotope of uranium. It has a half-life of 4.15 billion years. And the whole range of radioactive isotopes have half-lives in between these values. When I'm working on half-life problems, I can approach it a couple of ways. I can simply count out the half-lives and figure percentages based on that, or I can use a rate kinetics equation to help me solve it. If I'm just going to count out half-lives, I would take a look at something like element Z with a half-life of 3 days. I want to find out what percentage is left after 3 days. Half-life means I start with 100%. After one half-life, 50% of it is gone. So 3 days is one half-life, so I have 50% gone. After a second half-life, another 50% has decayed, so I'm left with 25%. I can keep going down and cutting my percentage remaining in half, and that would be one way to solve a half-life problem. Another way to take a look at this problem would be, I start with a mass, this time, of element Z, and I want to find out how much will be left after 18 days. 18 days is 6 half-lives, so if I want to do the counting down half-lives process, after one half-life, 50% is left. After 2 half-lives, 25% is left. After 3 half-lives, 12.5% is left. 4 half-lives, 6.25%. After 5 half-lives, 3.125% is left. And after 6 half-lives, 1.5625% is left. So now I know what percentage of my original amount is remaining. I can take that percentage, multiply it by my original amount, and that will give me the mass of my sample remaining after 18 days. I find I have 0.3125 grams left. Now the other way I can do it is to use the equations from kinetics. Half-lives of radioactive isotopes are first-order reactions for rates of decay. So I use a first-order integrated rate law, reorganize it a little bit so that it looks like this. So I have the log of my original amount over the amount that I'm looking for equals x, which is my number of half-lives, times the log of 2. Again, n sub 0 is my initial or original quantity. It can be grams, moles, percentage, counts, nuclei. N is the amount of my material at time t. Time t is the total amount of time that has passed since the beginning, and I find the total amount of time by taking the number of half-lives, x, and multiplying it by the time for one half-life. So to use this equation, I'm going to take the log of 20 over what I'm looking for. We'll call it x. That equals 6, which is my number of half-lives, times the log of 2. 6 times the log of 2 is 1.806. So now I have the log of 20 over my unknown equals 1.806. To take the inverse of each side, I'm going to take 20 over x, and that's going to equal the 10 raised to the 1.806 power. 10 to the 1.806 power is 64. So now I find that x is 20 divided by 64, and that equals 0.3125 grams. Same answer as before. So 2 ways that I can get to the same answer. Again, a reminder that radioactive decay is a first-order reaction, so my rate equation is simply going to be the rate constant times my quantity n. And the rate constant is the natural log divided by t1/2. Again, these are equations that we saw in kinetics. They're going to reappear while we're working with radioactive decay if we're looking at rates of those processes. Some practical applications for half-life and knowing how to calculate half-life. One would be as using radioactive materials as biological tracers. Many times they're used in plant studies to determine the uptake of nutrients. Sulfur is a common element in a number of amino acids, so if we can put a radioactive label on amino acids containing sulfur, we can study the plant's use of those particular nutrients. Two isotopes look like they're available to us. We have sulfur 35 that has a half-life of 87 days. We have sulfur 37 which has a half-life of 5 minutes. Now, if we're doing plant studies, we need to figure out which of those would be a better choice for us. In general, if we're dealing with plants, we want something that doesn't necessarily take years to break down, but 5 minutes is a little bit shorter, so which would be a better choice and why? Well, if we're studying plants, we want something that lasts days, but not necessarily takes years to break down. So we would probably go with the sulfur 35 because 87 days is essentially a summer growing season, and we could study the uptake of sulfur better with that type of isotope. Another way we can use radioactive half-lives when we're dealing with isotopes is to look at radioactive dating. Primarily archaeologists, sometimes geologists. Two primary isotopes that are used for this are carbon-14 and potassium-40. Carbon-14 is generated in nature, and it's generated generally when ultraviolet light from the sun hits carbon dioxide in the atmosphere and causes the carbon, that's usually a carbon-12 isotope, to take on 2 more neutrons that are floating around and becomes carbon-14. Carbon-14 enters the plants. Plants go through photosynthesis and put the carbon-14 into glucose. The plants get eaten by animals, and so that carbon-14 now gets into the animals. With carbon-14 in plants and in animals being present at about the same percent for each of them, the carbon-14 for both types of organisms gets returned to the atmosphere as organisms respire. By doing this, then, plants, animals, and the atmosphere all have about the same percentage of carbon-14 present. So we have an equilibrium going on. Now what happens when the organism dies? Well, it doesn't take in any more carbon-14, so the amount present can only decrease. So if we know the normal or the standard amount present in living organisms for that time period, and we can measure the amount of carbon-14 present in fossils or bones of a specimen, we can figure out its age. The half-life for carbon-14 is very well known. It's 5,730 years. We can figure out the age of an organic relic within pretty good accuracy as long as it's got more than 5% of the carbon-14 present compared to what was originally there. If it gets less than that, it's difficult to identify the organism's age. So what that means, if an organism is older than about 25 to 30,000 years, it's tough to age it. The problem that we run into when trying to date an organic remains material is if we have a very small sample, that means the carbon-14 present is going to be even smaller. And so it gets difficult to distinguish the carbon-14 from background radiation. If we have a very large chunk of sample we can analyze, we might be able to do better, but small samples, not so much. Potassium-14 is used to date very old rocks, so this is a geologist tool. The reason it's used is potassium-40 decays to argon-40. Potassium is a solid, argon is a gas. It's very unusual to find argon trapped in rocks, especially argon-40. If it's found, that's an indication that it came from radioactive potassium-40. So potassium is common in minerals. So if we find argon, little packets of argon trapped in minerals that are being analyzed, especially if it's argon-40, then we can deduce that it's from radioactive potassium, and we can determine an approximate age. But very old rocks, again, are what we are looking at. The half-life of potassium-40 is 1.4 times 10 to the 9th years, so it takes a very long time for it to decay.